Or no, this is an engineering hour session. Actually, good. That's Friday so this means we're hands-on today. I'm Braden Lewis, and I'm here with Umesh Lokhande for the session Ozone Advanced Graphical Debugging for Real-Time Embedded Systems. We're happy to have you with us. Umesh is going to introduce himself a little bit later, but first let's go through some housekeeping stuff. Today's session is about 45 minutes of presentation with 10 minutes of Q&A at the end of the hour, where we're going to be answering all sorts of questions on Ozone and advanced real-time debugging in the Ozone graphical tool. It's whoa, got some feedback here.
Mhm.
There we go. Okay, that should be better. No echo now. All
Yes.
right. So yeah, like I was saying, 45 minutes of presentation and about 10 minutes of Q&A at the end of the hour. If you are in the Livestorm meetup platform, I just want to take you around the tools. So in the bottom right, there's an icon that says chat. Navigate over there if you're not already there, and that's where your primary means of communication with us and with other attendees during the session. So you're going to be able to discuss, what Umesh is talking about around ozone, as well as put in questions and support tickets over there. So make sure you make good use of the chat section. And if you put questions in there early and often while we're going through the material, we'll make sure to harvest them, and I'll load them up so that Umesh is able to answer them at the end of the hour in the closing Q&A. There's also a questions tab that's just to the left of the chat tab if you look in the bottom right of the tool. So just the next tab over, you can put questions in there as well. So we're going to be taking questions from both those locations. And also, if you're on YouTube, Facebook, LinkedIn, streaming over there, just use the chat interface there, the local native chat interface for whatever application that is. Throw your questions in, we'll grab them, we'll get them to Umesh and make sure that they get answered as long as we have time to do so. If not, if we run out of time, please make sure to join us in the DevHeads Discord server, which you can get to by going to discord.gg/devheads. There's a community there where Umesh and a bunch of other embedded and IoT developers are ready to assist you with professional design challenges. So if you have any trouble or need tips, tricks, etc., feel free to go on over to the DevHeads Discord server, and we will do everything we can to collab with you and make sure to get your design on track. If you are having issues streaming, there are a couple of different things you're going to want to do. If you're in the primary meetup platform, all the way on the other side of the bottom navigation, there's a help tab. Click that help icon, and it'll open up a wizard that'll take you through various steps that can get you back online. Everywhere else, I would advise if you're in an app, try to use the browser instead of any like downloadable version, like a desktop app or something. That helps with versioning issues. And if you're somewhere where you're pulling lower than 5 megabits per second down off your wireless network or wired, I guess, you're going to want to try to get on another network because the stream might be difficult. Yes, and so anywhere you are, if you do have problems, put your issues into the chat channels, and we'll field them and we'll try to support. If you can't help yourself, we'll do our best to come through and help out. Only a couple other items here that the session's being recorded and it'll be available on the DevHeads YouTube channel under the live stream section immediately after the event. So if you miss anything, head on over there and you can check out all the good stuff from today's session. The slides are also going to be made available. We'll do our best to get them up into the handout section of this event. And then there'll be a meeting notes section over in the DevHeads Discord server, so you can dive into the server and get access to the slides. Same thing with any code that Emesh has from today. We'll throw it up into the GitHub, and you guys will be able to take a look at that a little bit later. And then finally, stick around at the end. We'll talk about some upcoming stuff that we have, events in the server. So there are a couple events a week, two to four a week every week. So Stick around towards the end and we'll let you know what's on the schedule. Well, that was a lot, huh, Umesh? A lot of stuff to go
Yes, yes, it's really not.
All right. Well, at least then we won't have tons of questions in the chat cluttering it up about administrative stuff. So now we can go ahead and hand it off to Mesh to go through Ozone Advanced Graphical Debugging for Real-Time Embedded Systems. Floor is yours, Mesh.
Hi everyone, I hope you all are excited to learn about Ozone, which is an advanced graphical debugger for real-time embedded systems. So today we're going to start off with an overview. Then we will talk about what is Ozone, why we need Ozone in the first place, and then we'll talk about how Ozone works. And then we will talk about how does Ozone project file work. So one of the greatest thing you can take away from today's session is this JDebug file, which is basically an extension for the Ozone project. And we're going to talk about it and really very much in detail, which you can't find much online anywhere. And then I will show you a live demo, debugging of an FreeRTOS task with an STM32F4 microcontroller live. This will be an hands-on. And then we will going to talk about the advanced debugging, like an instruction tracing, code coverage, and code profiling and stuff like that, because I think very many of you are excited to learn about what does this advanced debugging exactly means, and we're going to talk about it. And then we'll summarize all the things that we have seen so far. And towards the end of the session, I will take a question if there are any. And if we run out of a time, feel free to drop your question into the Discord server. So let's just talk about what is an Ozone. So it's a piece of software which will be used to already written applications. So if you have a software application which is already pre-written for a microcontroller application, I'm talking about microcontroller firmware, and if you want to debug, then Ozone will be the application that you can use. The great thing about Ozone is it is independent of programming language and the tool chain. So it doesn't matter whether you write your microcontroller firmware in C or C++, or even it support the Rust programming language. So if you're most updated person in the embedded systems, then probably you're using Rust and you probably want to debug your software application. So with Ozone, it doesn't matter which programming language you built your application and what kind of tool chain that you have used, but it pretty much support all the tool chains. No special code or configuration required. So if you have seen my previous engineering hour, we have covered the Sega tools like an RTT technology and then the system view. And you might have realized that in those cases, we have to instrument. So we have to port the source code that is given by a Sega to us, and we have to port that source code into our microcontroller project. Here, the great thing is in Ozone, we don't have to do any instrumentation. We don't have to port any code in our microcontroller program. So your code, your project, microcontroller project would remain as it is. We don't touch your code at all. Okay, that's a great thing. So everything happens is in to the Ozone only, right? That's a great thing. Then a scriptable project file to set up everything automatically. So whatever we do as a part of the debugging process, and debugging is very comprehensive skills, by the way, you can really dig deeper to the level to almost anything. Okay, and you can have a scripting file which is pretty much like a C style scripting. We'll get into that. That's what I say, like we will be talking a lot about this JDebug file, and that's the file we are talking about. So scriptable project file will file that we will set up and which will automate everything. And you have to note that one thing, that this Ozone software is tightly coupled with JLink and JTrace debug probe. That means if you want to use an Ozone software, then you have to have the official debugging tool like a JLink or maybe a JTrace debug probe. Now if you compare again with a system view that we have seen in the previous engineering hour for debugging, then we can able to use a system view even without having a JLink. So it can work with an ST-Link and it can also work with the UART, but this is not a case with Ozone. You need to have an official debugger. So it is tightly coupled with JLink and JTrace debug probe. And we're going to talk about it, like there are very many different versions of JLink and JTrace and how they differ and what kind of access you're going to get with those versions. We're going to talk about it a bit later. So now you know what is Ozone. Now let's just talk about why we need Ozone. So if you want to do an advanced debugging like an instruction tracing, then you must have to have a tool like an Ozone. Then we can do a live code coverage and code profiling. Now don't worry about it. We will talk about it. What is instruction tracing is all about, then what is code coverage and code profiling. This is all about getting your microcontroller firmware production ready, right? So there's a lot of things you can do, like you can remove the dead code using these techniques. Then you can just remove some kind of locate the code hotspots in your microcontroller firmware. These are advanced things. We're going to talk about it a bit later. And then the great thing about Ozone is you can also do a power profiling. And power profiling is very, very important when you are building an battery operated product where you want your embedded systems to run on a battery, and then you have to trace every line of code, every function on every task in the RTOS, how much power does it consume, right? So this kind of profiling you can do. And then one more interesting thing that I love about it, about Ozone, is you can have a FreeRTOS task view in conjunction with call stack view. And this feature is really important when you optimize your code at very advanced level. So let me give an example. So if you, whenever you create a task, let's take an example, FreeRTOS task. You allocate a stack for every task, and then sometimes what happens is we put the random size of the memory allocated for the stack. Now what happens is in our code and in our application, very often we don't use the entire memory that is allocated. So we have to track down and see if we can able to remove this memory, free this memory resource, so that we can better use this memory for other use in. So that's basically how you're gonna optimize your firmware, and that's what all Ozone allow us to do. Okay, and that's what we're gonna see it in the future slides. So now let's just talk about how Ozone works. So let's say we have a microcontroller, and probably you know this microcontroller, especially we are talking about the Cortex M microcontroller for this session. And the Cortex M microcontroller, STM32F446, and you probably know that Cortex M has this EDM, embedded trace macro cell. So it's basically a trace buffer. So to get the debug information from the microcontroller, we will get the trace buffer, means the trace data from, there are two ways you can get this. The one is you can get it from the ETM buffer, and ETM basically allow us to collect the trace buffer data, and that gonna talk to your JLink debugger. So it could be a JLink or it could be a JTrace. It's a bit complex, but just understand the microcontroller can give us this trace buffer data, that's an debug information, either from using the ETM, embedded trace macro cell. That's the built-in functionality of the ARM architecture, ARM core from the ARM itself. The second way is you can use this SWD or JTAG adapter onto the microcontroller, so you can establish the communication using this JLink debug probe or JTrace debug probe, and that could allow us to do a streaming trace. I mean, streaming the trace, and that's a trace buffer. So one is you can use an on-chip resources on the microcontroller, that is an ETM buffer, to collect the traces, means the debug information. The other one is we can have this trace buffer onto the JLink, that's an external hardware, not on the microcontroller chip, but on the hardware itself, and then pull it from the microcontroller and keep it into the trace buffer. And then this JLink or JTrace debug adapter will pass this information further, the trace buffer information, into the Ozone software, which is an host application. So I hope this is clear. There are two ways. One is if you can use an ETM, that's an embedded trace macro cell, then you're using an on-chip resources on the microcontroller to get the traces debug information. Otherwise, you can use the debug probe, and we will have the trace buffer on the debug probe that can collect the traces from coming from the microcontroller. Okay, now and the third way is we can use this JTrace Pro kind of advanced debugging probe and collect the data from the microcontroller, this debug information, we can collect it and throw it straight away into the Ozone software. So we are not using any place, whether it's an on chip or maybe on the debugging probe itself. So we are getting the data, trace data from the microcontroller and showing straight away onto the Ozone software. So there's nothing in between and it will be very, very fast. But in that case, this advanced JTrace Pro then uses an technology for communication like in gigabit ethernet and for USB 3.0 or something like that. I hope this is how this Ozone works. This is clear for you. Let's just talk about the Ozone debug workflow. The question come to the mind, like how are we going to incorporate our microcontroller project with the Ozone software? So first thing we have to do is we have to build an microcontroller firmware that's a part of our microcontroller project. And that will be happening in our IDE, microcontroller IDE. And that has nothing to do with Ozone, by the way. Then we create a file called JDebug file. And I told you JDebug file is the Ozone project file. It has this extension JDebug, and that's basically an Ozone file. And now you might wonder what is special about this file. This file is kind of scripting file, which uses a C-style scripting in which we can do a lot of initialization about the debugging. We'll get into that. But we built the project microcontroller firmware, then we create and load this JDebug file into the Ozone software. I will show you live just a moment. And then we set the breakpoint, just like in any microcontroller firmware, how we debug, we set the breakpoint, then we start debugging. We have a lot of different windows because this is a graphical debugging with the Ozone, and you can visualize very many things. And one of those things would be a data watch window. And then we can also visualize the RTOS window. We have a dedicated RTOS window, and there you can able to do an RTOS aware debugging. I remember in the previous engineering hours, somebody asked this question, like, what if they want to get a very finer detail of the RTOS? Let's say they want to know about the priorities of the task, or maybe they want to know about the events, maybe the states, maybe the mutexes into the RTOS. Everything you can able to track down there. Okay, so that's a great thing about this RTOS window. We'll get into that, by the way. So as I said, the one takeaway from this entire session is about this Ozone project file. And the extension for this project file is .jdebug. Okay, that's the extension. Now, this JDebug file is a Ozone project file that stores the setting and configuration of a debugger. So whatever debugger that we are using, that configuration we will be storing into this file, and this will be very much like a C style programming language. And that's where you see this function here. I only have taken one function out of quite a few functions into this file, but we'll get into that file a bit later. So there is a function that says on project load. So as soon as we load the Ozone project into the Ozone software from our microcontroller firmware, I will show you entire process in a moment. But as soon as we load our Ozone project into the Ozone software, this function get invoked. Okay, and in this function, we then have to mention, like in our microcontroller project, how are we going to collect the traces? And look at this line, it says set trace source. So the traces will be collected using SWO, serial wire output. Then the device that we want to debug is STM32F446RE. Then we have to mention what kind of interface between the host and the hardware, and that will be a USB in this case, because I will be using an STM32 nuclear board and connecting over USB cable to the host PC. I will show you a bit later. And then the target, how the target will connect to this debugging probe is over JTAG. And then what will be the frequency, 4 megahertz. Then we have to add few more things like an SVD file. Now, many of you may not know what is an SVD file. So this is a system view description file for every microcontroller. The microcontroller manufacturer give you a register information in the form of this SVD file. So if you go to GitHub page onto the ST Microelectronics, you can easily download this SVD file, and I just kept it into the project folder. Okay, but you should know one thing, that this information that is inside the SVD file is coming from the ARM itself, because ARM is the one who licensed the code to ST, right? So bit complex, you will get it sometimes from ARM itself, sometimes from ST microelectronics. I'm using ST's microcontroller. That's why otherwise most of the people host it onto the GitHub. And then you can see we set the OS plugin, and that's the FreeRTOS plugin. And for the architecture, CM4, that's a Cortex M4 architecture, because STM32F4 microcontroller inherits from this Cortex M4 architecture. And the reason we add this line of code, because we want to tell the Ozone project that when we debug this FreeRTOS application, this microcontroller firmware, we wish to do an RTOS aware debugging. So we can have a much more information about the RTOS that we want to debug, especially the task. And then finally, you might wonder, how would this Ozone software knows where exactly our file is, I mean the build output? Because remember I said, like, the code that we write in our IDE has nothing to do with the Ozone software itself. So on the STM32Cube IDE, when we write an application microcontroller firmware, the job of our toolchain is just to create an .elf file. Okay, not hex, not bin. We are talking about .elf file. And look at this. Here is the path wherein you see the folder, the project folder, and then ozone.elf. This is the build output from the toolchain. That's why you remember in very initial slides I mentioned Ozone doesn't care what programming language you wrote your application in and what toolchain you have used, because all what the Ozone need is this ELF file. And look at this entire function. The most important part is this one, because here we connect the Ozone software with, I mean, our microcontroller project with the Ozone software, right? So whenever we run the debug session into the Ozone, because of this path, Ozone knows where the build output is from our project. Okay, so that's how. So the code that we write is into the Cube IDE. That's our tool chain. And the another piece of software is the Ozone host application software. Now, because in the Ozone software, we import, or maybe we load this JDebug file, and in the JDebug file, we put the information about the ELF file that is generated from the microcontroller project. And that's how this ELF file will get into the Ozone application software. And in the Ozone, then we start debugging the application line by line. I hope this is clear, because for the first time when I was figuring out, this was a little bit difficult and crazy for me to recognize how it works. And everything else is just a configuration. You just tell what interfaces you're using, what microcontroller you're using, what frequency you want to communicate your debug probe with your microcontroller. That's all. So this project file, this JDebug file, is everything to work with Ozone. That's the only file that we write. And this file may not have more than maybe 50, 60 lines of code. Everything else is just commented, by the way. You can write more code and do more advanced automation, but I'm just talking about in a context of the project that we want to see today. So this is the JDebug file that been referred as a Ozone project file. Now let's just talk about what hardware we need in order to work with this Ozone. So the advanced feature, which is basically live instruction tracing and the code profiling, will be supported by a JTrace Pro. So I always recommend people, if they are interested in exploring the advanced debugging, like in instruction tracing, code coverage, code profiling, to get the JTrace Pro. And again, in a JTrace Pro, you have quite a few products like JTrace Pro for Cortex M, then you have a Cortex R, and it's like a different dedicated JTrace Pro for a dedicated architecture. Even they have a JTrace Pro for RISC-V architecture, right? So it doesn't matter. So get any one JTrace Pro if you are interested in exploring this whole thing. Otherwise, if you are using a JLink basic version, JLink Debug Probe, let's say EDU version or base or ultra version, then you have a limited feature. So in our case, we will be using an onboard JLink debugger, which is quite a bit accessible to everyone, and that's why I prefer to go with this onboard JLink debugger. Of course, it has a limited features, limited capabilities, but it really does the job, right? So you will see in a moment when I will show you live. By debugging the live project, you would realize what it is capable of doing and what it can't able to do, but not everything that you need all the time, right? So you can have almost anything. Just remember, even if you buy an official debug probe, if you have an EDU, base, and ultra, you still have a limited feature access. So if you are interested in Ozone's to use it at full of its ability, then make sure you get the JTrace Pro. Okay, so that's very important point to note. Otherwise, you might invest your money, you're gonna buy it, and then find out, okay, it just doesn't do what it's supposed to do, right? So just make sure you compare all the products and features. So for us, today's session, what I will be using as my hardware setup. So we have this STM32 Nucleo board, and probably everybody knows that this Nucleo board has this ST-Link debugger here. So we will be debugging this STM32F4 microcontroller, which is a Cortex M4 core. And this ST-Link debugger, because we're gonna flash the J-Link firmware, this ST-Link debugger will be acting as a J-Link debugger. So we will create a link between this J-Link debugger to the host PC on which we are running this Ozone debug software. And by the way, in Ozone, you don't have to write any piece of code. It's just an dedicated standalone debugging software. And that's the beauty about it. So there's no cluttery window all over the place like your IDE where you write the code, where you debug the code and do a lot of things and pretty distractive. So Ozone is a dedicated piece of software that could allow us to do just the debugging. And we will be using a J-Link. Don't confuse, even if I mention here JTrace, that's the recommended. You can use a JTrace Pro, but we will be using a J-Link. And by the end of the session, you would know what is maximum possible with the onboard J-Link, right? Because there's nothing about as such in terms of debugging, like how much you can extend the debug capability of onboard J-Link debugger. So we will going to do it today. So that's the setup that I will be using. And then now you might wonder from where you can download this Ozone software. So you have to head over to thesecond.com as a website. And then on a top menu bar in the download section, you will get this Ozone J-Link debugger software, and you can get the latest version to be downloaded. It's pretty simple, like just download it and double click and just follow the instructions on the screen, and then you will be done. And even in the name itself, they say the J-Link debugger, right? So it's pretty confusing, but yeah. So, but I recommend you to use it with a JTrace Pro for advanced features. So once you open your Ozone software application, then it looks something like this. You can see on my screen, you have an code profile window where you can have all the code with the functions. You can expand it. I will show you a bit later. Then you have a watch window. Then you will have a dedicated place where you have a code where you can put the breakpoint. Now, one more thing, we didn't talk about it, but very, very important, that the great thing about using Ozone with the J-Link or any kind of official debugger is you can have an unlimited breakpoint, right? Otherwise, if you use an ST-Link debugger or something, you have a limited breakpoint you can add. Here you can add a multiple breakpoint, and pretty much they claim it unlimited. You have to check, but you can have a plenty of breakpoint in your code. And I managed to put two, I mean, just to demonstrate the capability. And then you can see here is a FreeRTOS window. Follow my mouse cursor. And this is what I was talking about, the FreeRTOS task view, wherein we would able to do an RTOS aware debugging, and we will collect all the information that we need from our RTOS application. So we can literally have an information about the priority, mutexes, and all this feature. You can go as much detail as you want by configuring your JDebug file. But basically, I already have shown how you can configure. The way you configure RTOS aware debugging in the Ozone software is by just adding FreeRTOS plugin, and that we added one liner into the JDebug file. And then you have this disassembly and other windows. I think this would make more sense when I will show you live. So let's not waste the time and go to the project. So I have this STM32 project created, Ozone, in the project pan, you can see. And let me first explain what this project is all about. You should understand one thing. This Ozone project is very elementary sort of FreeRTOS application. There's no special file that I have added from the Sagar. If you compare with an RTT technology and the Sagar system view, we need to port the source and header file into our microcontroller project. Here we don't have to do. This is very typical STM32 microcontroller project in Cube IDE. That's it. It has just the FreeRTOS port. That's it. That's why in the code you can see there's a FreeRTOS header file, task, and queue, because I'm using this queue. And if somebody doesn't know what is queue, then we have done a dedicated session about inter-task communication a couple of months back, and there I spoke about queue. So I will be using queue because I will be setting up the project where there will be a two task. One will be a producer task and second one will be a receiver task. And today we will be communicating a producer and receiver task, so they will be sharing the information in between and they will be using a queue. Probably you will see on the YouTube channel of the DevHeads, there's a dedicated video for it. But let's look at the logic a little bit in order to understand when we will be debugging the application. So we have this function, I mean, basically a task, start consumer task. And this basically, consumer task basically receives the data. So here's a variable that's receive data. And there is a producer task, which basically produced the data. So it's just a variable data initialized with a value 0. So what it does is this task producer task produce the value like 0, 1, 2, 3, 4 incremental value, and that incremental value will be received by a consumer task, and that will be stored into this receive data. So there is a produce data from the producer task, and there is a receive data into the consumer task. So this will be sending data to the receiver task, right? So the producer will produce the data and receiver will receive the data, and then we will be monitoring into the debugging. Now you will say, okay, this is so simple, why are we wasting our time here? Let me talk a little bit about it. So we put the delay of 500 milliseconds. So when producer produce the value, produce data, it will be creating maybe a 2 data points, okay, because there will be a 2 times this data will be incremented, because it has a 500 milliseconds delay, and in the receiver is receiving after 1 second, okay, because there is a difference between 500 milliseconds. There will be a 2 data point will be generated by a producer task, right? You will get into that bit later if it's confusing, but this is the project that we have set up. Now remember one thing, I said all what we need to do from our IDE is just to build the project. So when we build the project, let me build. Okay, you see 0 error and 0 warning. And then we have to go to our project folder, and here's the project folder. And under debug, we can able to see this ELF file, right? So this ELF file, and this is, if you want to confirm it, let me show you. Let me just right click on the project and then clean the project. And then you see the ELF file is gone, right? So let me go to my project and I build the fresh code. So once the build is finished, the ELF file will get created, generated. It will be a fresh new ELF file. So now if I go to folder, you see the ELF file show up here, and this is the time. It's Indian time, by the way, but it doesn't matter. You can trust me. This is the ELF file. Now let me clarify these things. We are using ELF file. We are not using hex file or bin file, because the ELF file can able to give us the path and pretty much access to the folder from the project folder. So this path, look at this carefully. c/user/desktop project folder and debug, this ELF file is located to. And if I open this JDebug folder, that's devheads.jdebug, and this path is same as the freshly created ELF file. And I already explained this entire function, by the way, if you remember from the slide, right? I'm just trying to put things in perspective how this Ozone software connect to our build output that is an ELF file, because that explanation I didn't found anywhere, and that I wanted to give you here today. So by putting this path here, our JDebug file, when it will be loaded onto the Ozone software, can find where exactly our project is located, and that is this Ozone project on my desktop, right? That's the path that I talk about. Now let's just not waste your time and get to the Ozone. So here's the Ozone software application. Let me open it up, and when you open, this is how it looks like. And all what we need to do is we have to click on open existing project, and then we have to import the JDebug file. That's what we were talking about. It's the Ozone project file. Okay, and that's the file that I have opened up into the Notepad++, and I showed you the path of the project where our build output was .elf file from our project. So let's select the .jdebug file and then click on open, and entire source code will be imported here. Look at this, right? So this was our project, and that's why we don't have the hex file or bin file. We have a ELF file. You can later read about why the significance of ELF file, but it supports ELF, and there's another one more extension called dwarf, DWARF. It's a debug special extension, but I don't want to distract you. So we will be using .elf file, and using this ELF file and JDebug file, which is a scripting file, JDebug file, we imported everything that we want from our microcontroller project. Now let's just talk about what we get once we import this JDebug file. And by the way, you will get my JDebug file from the GitHub page of the DevHeads, and you can then modify if you want. So here you can see the window that is a code profile window. Then you can have here a watch window. So here in the watch, I have added produce data variable and the receive data variable. And in the project, remember what I said, the produce data will be a value that will be produced like 0, 1, 2, 3 something, and this receiver will be receiving and storing into the receive data. So that's why we are monitoring in the debugging the both variable, produce data and receive data. And then you can, that's why I added the difference between a delay of 500 milliseconds and 1000 milliseconds, because when we start debugging, you can able to see the difference, how the value getting incremented, right? So you can now can correlate how the code makes the difference when we debug the code. And you can see on our program, we added one breakpoint, which is at this line of code where we are basically reading the data from the receive data variable. And another breakpoint I have added to the produce data. So this one where we print the produce data. And just to quickly remind you, that's why we use an official debugger, because we can add a multiple breakpoints. And sometimes if your code is so complex, my goal was not to make this code very complex to confuse you and make this whole event as a sleepy session. So I just only use 2 breakpoints. But if you have a multiple breakpoints, that can also be possible with the Ozone and with the JLink and JTrace. Okay, so I added this 2 breakpoint here. Then you can able to see top right corner, we have an FreeRTOS window where we can monitor the task. And let me just expand it here. So there's a disassembly. I'm not gonna waste so much time here. Let me just uh, click on the top left corner this icon here, and then I would select download and reset. So this is where the code will be flashed into the microcontroller memory. So let me click on download. And because my nuclear board is not connected, so let me just connect the nuclear board. And now I click on this debug button and then say download and reset the program. And then it says licensing term. I click on yes, I agree the licensing. Then it again asks me for some terms to accept, and I say accept. And now we are into the debug mode, and the code execution is here. And there's no value for produced data and the received data, and there's no information from the FreeRTOS. So let me just click on this run button. So it will resume the program execution, by the way, and then it will jump straight onto this line of code where we put the breakpoint. And now you see the produced data value is 0, right? That's exactly what we are expecting because the code is just started executing. And look at this RTOS aware debugging, okay, wherein we have a producer task and consumer task, and we can live see now the producer task is executing. That's why the value of producer task is 0. Now let me step through the code, okay, and now you see the date, the number value 0 goes into the received data. Let me step further, okay, as I click this button, go to next line, you can see the value of produced data and received data is changing, right? And you can also see this status is updating. The priority, I keep it low. Let me just expand a little further for you to understand. You can see the mutex count and stack information, everything. And I already spoke about the information, and the size of stack is very important when you optimize your code for a better resource and performance. So this is how your data will be tracked into the debugging. And at the same time, you can monitor your task states, how this task states get changed. The one thing that I wanted to show you here is if you go to view on a top menu bar, you can see how many features that it has. So especially we will focus on the advanced debug capabilities, and we talk about this code profile window, data sampling window. The one thing though you may not have seen very many places is this power sampling. And this power sampling is very advanced feature because you can able to track the power consumption here, and it will be happening on the source level debugging, because you will be knowing exactly when a particular piece of code is executing, how much that piece of code, that task, say for example, consume the power. And that is amazing information. Let me just open power sampling. So you can see the power sampling window show up here, and sampling frequency is 0. Let me just stop the debugging and make the sampling frequency as 1 kilohertz, because I want to show you how you can read the traces and the power information. So then let me just click this button and say download and reset. It will ask me again because we are loading the firmware again into the microcontroller. Click on accept, and then let me run the code. And now you see the information came up, like how much power consumption has happened, right? And now look at this. The code execution is at line number 66. So the code is executing, this microcontroller is executing this start producer task, and you can able to see how much the data it has collected. Let me just click on this because I want to show you live capturing. Okay, let me stop for a while. And by the way, just to clear this, if you are using a JTrace Pro, then you don't have to really do all this crazy thing, because you just connect and it takes care of everything. You just connect your debug probe and it takes care of everything. So let me download it again and accept. And now let me You see, it's live capturing. I hope you can see the small numbers here, and it will be constantly capturing the value. Now it capture and then it stops. I can stop debugging. The reason is because if you remember the presentation where I spoke about how Ozone works, when we use a trace buffer to collect the data from the microcontroller, and that too we are using the on-chip trace buffer. In the debugging, the on-chip trace buffer has very small size. That's why people pay huge money for this expensive debugger, right? Because either you then will have to have a bigger size of the trace buffer that is probably onto your trace probe, or it could be directly into the host PC. So it will take directly the space from your computer, and the Ozone will take care of that. If you're using microcontroller resources, then you will have very tiny bit of memory to be accessible to store your trace information that's in the trace buffer. And we talk about ETM, and when you use an SWO for the debugging, so if you look at the JDebug file, we are using SWO traces, serial wire output. So this uses basically an ITM traces. So it has nothing to do with ETM, wherein the reason why we have a limited capability is because of we are using an on-chip buffer, right? When you have an official debug probe, that debug probe must have to support the ETM feature onto the Cortex M architecture from the ARM, right? That's again one key point that you have to note. But we don't want to get into that. It would be too much into it. But let's come back to the power consumption, because I know that many of you are building an IoT application, and for IoT application, and if you are working on resource constraint, then the power is also be a problem. So the great thing is you can export this data. Let's say if you want to export this power traces later for analysis, you can just right click and click on export here. Let me click on export, and you see Ozone power sampling. I can just store it onto the desktop and click on save, and let me, you can see it here as well, but you can also see the freshly created CSV file that you can just double click and open and access the data as simple as that, right? And then you can analyze later further whenever you want, right? So that's great thing about this debug probe, right? One more thing I want to get to show you. Let me just create a little bit of space. Okay, so this assembly window, and I have to pull it down because we are interested in monitoring this disassembly window. Then this is an actual source code that we will be debugging, and this is the code profile. In the code profile, you in fact can able to see the task that we have created. I hope I will find it pretty quickly. Look at this. I can expand and I can see every bit of a thing, even the breakpoint into this. You can even expand this and you can see the instruction assembly instruction into it. And when let me just run debug again to show you some magic here. Accept. Now look at this. Whenever I step through the code, this cursor, this execution is moving, and this is also moving, right? So everything is in a sync, right? You see? And the task is also updating at the same time. So if you have a live instruction capturing using, let's say, a JTrace Pro or something, then you can able to see everything running so fast and live in the runtime. We don't actually need it for analysis. You still can able to analyze with the J-Link hardware, which is what we are doing right now. But that is what you can able to do as an instruction tracing and the the code profiling and stuff like that. We'll talk about it a bit later, but this is how you can able to analyze, debug your microcontroller firmware. Let me just stop debugging, and I hope I have not forgot anything. There are a lot of different windows. That's why I took you to this view, and I talked about this many things. There's a timeline window as well. So in the timeline window, we can able to see the task execution here. There's no point to waste the time here right now, but you still can able to see the task execution in the runtime. So probably you may remember from the previous system view, you can, the system view is more efficient in case of visualizing the RTOS task, no matter which RTOS you use. But yeah, these are the windows and graphical visual way how you can debug and you can control pretty much everything that you want in your microcontroller firmware application. So let's go back to the presentation, and let me take you to the slide. That's where we talk about the ozone window. And let's just talk about advanced capabilities. So there are two things we didn't talk about. And those two things I want to talk right now on the slide. Something called code coverage. In the code coverage, you may remember when I expanded the code profile window, there will be a line number and there will be a functions with the C code, the source level debugging. That's why we can able to see the debug breakpoint, the breakpoint into a particular code, which is even in the assembly and C source. Now, what happens is when you do a live code coverage, you can have an access to this color codes, which is onto the left side of the window. And this color code tells us how we're going to optimize our code. So let's say this green, I hope you can see it's a green, it's a light green color, but it's a green. So this piece of code, these instructions are very, very important. That means they are executing right now. Okay, so you can't able to remove anything or optimize anything. There's no scope. There's in yellow, which you can uh, you can you can probably see there are yellow traces. So the way you can follow the documentation, there is a green, orange, and white. So if you have a code which is a white labeled here, I took this picture from the the knowledge base of a Sego, but you can remove those lines of code, right? So now why am I explaining these things? So when you write your microcontroller firmware, and I'm talking about a very complex microcontroller firmware, I'm not talking about maybe 5 source files, maybe quite a few header files. No, I'm talking about really, really complex. In a complex firmware, a lot of code that we write that never executes, right? Or it barely execute in the lifetime of the application. And we have to track down that code. Basically, what I'm trying to make my point is you can locate the dead code in your firmware, and you can also locate the hotspot. Why? Because you have the live code profiling feature, and in live code profiling, you know which code is executing, how much it is executing, how often it is executing, and how much load it is creating in your microcontroller. I hope this is clear. If the more load it gets created, it will consume more power, right? There are a lot of crazy things associated with this, but this is all correlated. And if you manage this whole thing, you basically end up optimizing the performance of your microcontroller firmware. That's why more than just a bug tracking, I mean, you can say the ozone is great for tracking down the infrequent, maybe hard to reproduce bugs or something. But I would say ozone is also great piece of software to to satisfy your regulatory requirement. So you probably need all over the places a proof of the performance of your operating system, your application, microcontroller firmware. And because you can export every bit of data. I showed you live how you can export. I showed you the power consumption, how you can export. But similarly, you can export anything, any information that you want. And you can attach this documents as to satisfy your regulatory requirement to get your product certification or stuff like that. So it's pretty advanced stuff. That's why I think the investment that you put buying that hardware worth in the end. All right, so that's all about it. You can see here, this is called execution. This is not execution counter, by the way. There's one more concept called execution counter, but probably we'll have some another day, another advanced session about it. But in this picture, in live code profiling, you can see if we just take the mouse cursor in the debug window live, then we can able to see how many time this code been fetched. So you can see the exact number, then how many time it will be executed, then how much load it is creating onto the microcontroller CPU and some memory and stuff like that. And then you can understand you can literally do a profiling of your controller. I hope this gives a pretty detailed understanding what does it means advanced debugging, right? Advanced debugging means taking care of all these things which makes your microcontroller firmware the greatest and the best firmware. So let's just summarize all the thing. I think we are already running out of time. So the way I would put up this is this Ozone is all-in-one solution. So you have one Ozone software that can take care all the requirement for your advanced debugging. Then it would also help you as a performance analyzer. It's more than a plain debugging. That's why I said you can do a lot more than just a simple debugging here in the Ozone. And believe me, we haven't even yet seen maybe a 30 or 40% of its capability. There are a lot of things you can track down, the hard faults and other memory faults and crazy things. Then this Ozone will help you to get the system inside, analyze the runtime performance of your RTOS, especially when you want to do an RTOS aware debugging to this finer level. That's why I showed you, you can literally be able to track all the information into the free RTOS window of the Ozone software. So you can see the priority live, you can see the status of the task and mutexes, counts, even how much memory that it consumed, right? So you can know how you can free it up. You can know which task the system halt at because you can live monitor it, what other task currently doing because you have a multiple task into the window, how much stack it is allocated to, so you can free up the space in case if there is a possibility, because you know, as an firmware developer, you know how much memory your controller has. So you can always have a scope to optimize it because you know firsthand information how much your task is using into your microcontroller to get the firmware working. Then you can automate your setup because we talked about it. You have this Ozone project file, which is kind of a scripting file, C style scripting file, and you can add a lot of different functions. You can read the Ozone official documentation from Sager in order to get more details about it, but you can do a mm, lot of great things with with the JDebug file by just extending the capability. Our goal was just to perform the debug functionality, not the production level uh, debug or maybe a programming feature. But that also can be done. And a lot of automation is possible by configuring with GUI and stuff like that. And I talked about it earlier that it can provide you unlimited flash breakpoints because if you just do a generic, if you use a generic debugger, then you will have a limited number of breakpoints that you can add when you debug your application. I hope this helps you understand how the Ozone and the J-Link and J-Trace works. The J-Trace, we didn't use it, but it's really not needed. I wanted to get everything on the J-Link. So I hope you have found this session educational and entertaining. Thank you.
Great. Good stuff as always, Amesh. So for everybody, we're kind of out of time, but I did want to let you guys know that if you do have questions, there are multiple ways to engage professionals like Amesh and others. You can go to the DevHeads Discord server, which I mentioned in the chat above. You can also head over to the DevHeads website, which you can get to by going to https://devheads.io. We are making some updates there, building out more development tools and resources for all of you guys. So lots of good stuff in store. Also, there is the sign up page for future events. You want to check that out on Livestorm. I just dropped links to all of those things in the chat. So really great session. Really happy to have Emesh as part of the community, and he's a resource that we and you guys too should all appreciate and take advantage of. Until then, we've got some sessions next week coming up on Embedded C, and also some hands-on demonstrations that are dealing with some high-performance computing platforms and getting Yocto running up on them. So we look forward to seeing you all at those sessions and in the community. Thanks so much, Umesh. Great
Thank
session
you.
as always. And everybody, have a great weekend.
Thank you. Bye bye.